Hello, my name is David Themens, and I'll be talking today about the ionosphere, how it behaves and its dynamics, what that means for communications and navigation systems. So I'll start off by giving you an introduction to the ionosphere, then talk about how the sun and the variability of the sun, namely solar activity, affects the ionosphere and its dynamics. Then we'll talk about how the ionosphere interacts with radio waves and why we care about it, before discussing how we monitor the ionosphere and how we model it. Before I'll finish off with a brief discussion about the direction forward. The ionosphere is a layer of plasma embedded in the upper atmosphere between roughly 80 and 2,000 kilometers altitude. It's predominantly produced by photoionization of the upper atmosphere by energetic photons from the sun. And by virtue of it having high electrical conductivity, it interacts very strongly with the Earth's magnetic field, producing dynamics that are much more complicated than one would expect from a region of our atmosphere. On the right, I just have a little demonstration where when we talk about energetic photons from the sun, I'm not talking about infrared radiation. Infrared radiation is mostly responsible for the heating of the Earth's surface. Visible light, similarly, goes all the way through the atmosphere and is responsible for most plant life on Earth. In the near ultraviolet, that radiation tends to be absorbed by ozone in the upper atmosphere, and hence why we care about the ozone layer. What I'm really talking about is the far ultraviolet and the extreme ultraviolet band of solar radiance. So these bands of solar emissions are sufficiently high in energy that they ionize molecular constituents and atomic constituent molecules in the upper atmosphere. Things like N2, O2, and atomic oxygen. If you go further past the extreme ultraviolet, you arrive at X-rays, where X-rays, in fact, penetrate all the way through the ionosphere to the lowermost regions of the upper stratosphere, and can produce ionization at fairly low heights, causing severe blackout conditions for high-frequency communication systems. So when I talk about the ionosphere being embedded in the upper atmosphere, what I really mean is if we look at the density of different species, either molecules or atoms, in the upper atmosphere, given here in terms of altitude and density along the x-axis, you can see one, the atmosphere decays exponentially as you increase in altitude, and two, if you compare the densities of atmospheric constituents to the densities of ions and electrons in the ionosphere given here, you note that really there are fundamentally fewer ions and electrons, or far less plasma in the upper atmosphere than there is neutral atmosphere, or rather thermosphere. The ionosphere, the lowermost layers, are mostly made up of molecular ions, so NO+, O2+, N2+, produced by photoionization of N2+ and O2+, or N2 and O2 in the lower portion of the ionosphere, below about 150 kilometers or so. Above that, the predominant ion is O+, or atomic oxygen ions, which occupy the peak density of the ionosphere. Above the peak into what we refer to as the topside ionosphere, O+ ions cede their dominance to hydrogen ions and helium ions, which dominate the layer above about 1,000 kilometers, and we typically refer to that as the plasmasphere. So from my description so far, you can tell that it's actually quite challenging to discuss the ionosphere without first having a discussion about the sun. The sun goes through a number of variations, some of which you might be familiar with. For example, it goes through what we call the solar activity cycle, where at low solar activity, the sun looks fairly plain and unstructured, whereas at high solar activity, or what we call solar maximum, you can start to see the appearance of a number of these structures on the sun that we call sunspots. These are regions of where the sun's magnetic field is penetrated up through the thermosphere and are highly magnetically dynamic regions that tend to be the source region for a lot of energetic events that can deeply affect the ionosphere and our upper atmosphere. This cycle generally features the creation of these sunspots around the 30 degrees off the solar axis at the beginning of the cycle, solar equator, sorry, which slowly begin to be produced closer and closer to the equator before eventually decaying and being left with very few sunspots. The maximum in any given cycle is usually in the intermediary between this original creation of sunspots at around the 30-degree latitude of the sun and the eventual decay of the sunspots at the solar equator. The bottom plot here is just a demonstration of the 11-year periodicity of the total area occupied by these sunspots on the solar surface. So you can see every 11 years we go through this fairly consistent cycle of increased variability followed by a lull in activity. So you might ask why we care about sunspots. Well, the sunspot cycle, or the number of sunspots on the solar surface, is directly coupled to the radio emissions from the sun, as well as the extreme ultraviolet and far ultraviolet emission from the sun. And so, since we know that these ultraviolet emissions, or these extreme ultraviolet emissions, are responsible for the ionization of the upper atmosphere, this solar cycle becomes an integral part of the variability of the ionosphere. So, if we look at just the regular variability of the ionosphere, at solar maximum, given by the solid lines here and here, the electron density, or the plasma density of the ionosphere, is substantially enhanced with respect to the density at solar minimum, given by the dashed line here and here. The red curves correspond to nighttime, and the black curves correspond to daytime conditions. You'll note that during the daytime, when we have a substantial amount of photoionization, the ionosphere can be broken up into a series of layers. We have the D region, the lowermost region of the atmosphere. This is generally the region that we attribute to absorption for high-frequency communication systems. Above that, we have the E region, which is mostly made up of molecular ions like N2+, O2+, and NO+. Above that, we have the F1 layer, which is the region where we have the maximum photoionization in the ionosphere. And finally, above that, we have the F2 layer, or the F2 region, which coincides with the maximum electron density, or the maximum plasma density of the ionosphere. Above this peak, the ionospheric electron density decays exponentially into a region we call the top side. You'll note that during the nighttime, even though we don't have a source of photoionization, because the rate at which the electrons and ions recombine in the atmosphere is related to the density of the regular atmosphere, the neutral atmosphere, the lowermost region of the ionosphere decays very rapidly when you no longer have a source of photoionization. However, when you go up to higher altitudes, where the abundance of neutral molecules and atoms is substantially lower, the ionosphere can actually persist throughout the night. And this actually becomes an important or helpful feature of the ionosphere, in that if we want to use the ionosphere for something, it's nice to know that even when we don't have photoionization, when we don't have a source of ionization, it's still there. So that's the kind of quiescent normal variability of the ionosphere. However, the ionosphere also can exhibit a fairly dynamic behavior in the presence of strong, what we refer to as geomagnetic storms, which are caused by storms or eruptions of plasma of the sun. And so here I just have a quick video of what we call a coronal mass ejection from the sun, where you see this loop of plasma surrounding the sunspot region here is ejected from the solar surface out into the interplanetary medium. This will repeat in a second. These are just different coronagraphs or different wavelengths that we're looking at this emission. You can see a little bit more clearly just how massive of an eruption of plasma is coming from this coronal mass ejection. There was also another satellite that was available during this period called Stereo, which was able to look at the CME from a different angle from the side. And it really gives you an impression of just how impressive an ejection of mass this is. To give you an impression of scale, this is the Earth at scale with respect to this loop of plasma that's on the Earth, on the solar surface. So these coronal mass ejections are massive with respect to the Earth and can cause significant disturbances within the ionosphere. So when one of these coronal mass ejections occurs, if it's directed towards the Earth, the embedded magnetic field of this plasma is oriented southward with respect to the Earth's magnetic field. The magnetic field lines of the plasma ejected from the sun can connect with the Earth's magnetic field and drag it into the night side or into the unsunlit side of the Earth, where it'll eventually reconnect in the tail and inject energy into the plasma in the tail, causing a precipitation of particles towards the poles of the Earth, which we refer to as aurora. This is just going to be a video of some aurora at Yellowknife to give you an impression of what we're talking about here. So there's a bit of cloud initially, but you can see eventually the aurora kind of prevails over the cloud. And you can see these really dynamic and kind of fascinating structures that move through the field of view. These aurora are produced by those energetic particles being accelerated in along the magnetic field and colliding with our Earth's upper atmosphere. And the process of that collision, those particles also ionize the upper atmosphere, where the depth at which these particles create ions is dependent on the energy of those, or the speed at which those particles are moving. Very fast, very energetic particles will penetrate deep into the atmosphere and deposit their energy or cause ionization down into the D region ionosphere, which can cause a significant absorption of HF Rios communications, which we'll talk about in a few minutes. You'll note that even very low energy precipitation or particle precipitation can cause ionization in the upper atmosphere at the region, even to the F region of the ionosphere. What this means in terms of that profile of the electron density that you're imagining before, which is roughly given by this blue line here, is that ionization causes a substantial enhancement in the electron density and ion density or plasma density of the ionosphere given by this black curve here. Similarly, in this situation, where the red curves are actually a model that I made that I'll be discussing later. Unfortunately, the complexity of the ionosphere doesn't end there. The ionosphere is a horribly or maybe fantastically coupled system where we have photoionization from the sun, solar energetic particles, we have interactions with the Earth's magnetic field, we have interactions with the atmosphere below us where large convective systems like thunderstorms can generate waves that propagate up into the ionosphere and cause disturbances and create structures within the ionosphere itself, and can modulate the upper atmosphere. So it's an incredibly complex system, and when you think about it in the context of say how we model weather in our regular atmosphere, you can imagine that the additional complexity leads to some fairly substantial problems in terms of predictability. So if the ionosphere is so complex, why do we care? Why do we bother trying to model it? Why do we spend so much time looking at it? Is it just because it has some shiny aurora that we're drawn to? The reality is that the ionosphere acts as a medium and reflecting surface for high-frequency radio communications. These are communications in the band between 3 and about 30 megahertz, which are standard in the aviation industry as a backup system. This is particularly important when you have transpolar flights that rely on these systems for communications in the absence of ground infrastructure to tell or to monitor and report the position of an aircraft. If these communications are unavailable, say because of an X-ray flare that enhanced ionization in the D region and caused a complete blackout of HF communications, those flights are required to be rerouted at a significant cost to the airlines. Similarly, by what I mean in terms of a reflecting surface, if the frequency that you're transmitting is sufficiently below what I'll refer to as the plasma frequency of the ionosphere, which is just proportional to its electron density, I won't describe it any further than that, a signal propagated up towards the ionosphere will become reflected. This means that you can have extremely long-range communications by bouncing signals repeatedly off the ionosphere back towards Earth, towards whatever friend you have in Australia or Canada, maybe. This also enables technologies like what we call over-the-horizon radar, which are were popular Cold War radar systems that operate in the HF band and use the ionosphere as a mirror to look around the Earth's horizon. Normal radars can get you or can tell you a target's position out to about maybe 200 kilometers. An over-the-horizon radar system can tell you the position of a target out to several thousand kilometers. In some cases, up to as much as 5,000 kilometers. This is particularly relevant when we start talking about areas that can't have large networks of monitoring radars, such as the high Arctic, where there isn't ground infrastructure to facilitate the development of such a network. So if you have one over-the-horizon radar, you can monitor a significant portion of the Arctic without having to have expensive networks of these radars. Not only does the ionosphere affect the high-frequency band, but it also affects signals in what we call the ultra-high frequency, or the UHF band. These are signals in the low gigahertz range, in the low end of the microwave band. And what happens is, as a signal propagates through the ionosphere, it can become distorted. It can be scattered by structures within the ionosphere, and it can be slowed down. The slowing down of the signal becomes a significant problem when you're trying to use navigation systems like GPS that relies on the assumption of the time of flight of your signal being related to the distance between the satellite and the receiver by the speed of light. If the signal isn't propagating at the speed of light, you'll cause a significant error in your ability to determine your position. For the same reasons, these irregularities in the ionosphere and this delaying as signals propagate through the ionosphere can cause distortion in radio telescope imaging from the ground. So if we want to effectively use these technologies like GPS or over-the-horizon radar, we need to model the ionosphere. Now, there are two main kind of regimes of ionospheric models, namely empirical models and physical or physics-based models. Physics-based models are incredible scientific tools that require very intricate knowledge of the physics at play in the ionosphere, which unfortunately for the ionosphere is still somewhat under research. Careful information about the drivers of the system, which for the ionosphere is also highly undersampled, and information about the boundary conditions around your model. We need to know what the forcing is, or what waves are coming up from the troposphere, stratosphere, mesosphere, and how those waves are coupling with the ionosphere in our model. And so, physics-based models, due to the complexity of the system, have traditionally had trouble being an accurate representation of the ionosphere for operational purposes. And so, because of that, very often we've seen the development of these empirical models, which are just fits of various mathematical functions to large databases of data or measurements that we have of the ionosphere. And so what I'm going to focus on from here on out are these empirical models. So empirical models of the ionosphere have been around for quite a while. They tend to come in two flavors. There are global models, the most famous of which is the International Reference Ionosphere, which is recognized by the International Standards Organization as the global standard for ionospheric specification. There's also the International Center for Theoretical Physics, ICTP's NE-QUIC model, which is the kind of go-to favorite model of ESA, and a version of which is the correction model used by Europe's Galileo navigation system. There are also regional models, like the empirical Canadian Hierarchic Ionospheric model, which is the model that I developed as part of my PhD and postdoctoral work, as well as the simplified ionospheric regional model, or CERM, that was developed at the Italian National Geophysical and Volcanology Center. So, unsurprisingly, I'm going to talk a little bit about eShame. So, eShame was built on a large database of ionospheric observations that stretched back all the way to about 1939, where we had the original observations of the ionosphere in Slough in the UK. Ionosomes are high-frequency radars that play on the principle of reflection from the ionosphere to bounce various high-frequency signals in a range of frequencies from, say, 2 to 30 megahertz off of the ionosphere until they no longer get reflected. They then invert these echoes into a profile of the electron density of the ionosphere that's available up to the peak density of the ionosphere. Here we just have an ionosome that's located in Pond Inlet in Canada, where this is the transmit mast, and you can see a few of the receivers on the ground here. So by a lot of these ionosomes, I mean that we've gathered about 80 of them from all around the world, dating again back to those original 1939 observations in Slough. And you can see generally over land we have a very good coverage of observations. at least for the electron density of the ionosphere, up to that F2 peak because of these ionosomes. But ionosomes are restricted to propagation below that peak density. And so if you want to look at the density of the ionosphere above that peak, you need to use something like an incoherent scatter radar. These are megawatt VHF radars that transmit high powered signals up towards the ionosphere and measure the scattering of these signals off of the free electrons that in the ionosphere. By doing this, these incoherent scatter radars are able to give you a profile of the electron density or the plasma density of the ionosphere from about 50 kilometers in some cases, all the way up to anywhere between 600 and 3,000 kilometers altitude. So these systems cover a much wider range of altitudes than those ionosomes. The problem, of course, is that these are incredibly expensive systems costing millions and millions of dollars. And as such, there are really only about 8 of them in the world at any given time. In addition to those incoherent scatter radars, you might think, well, why don't we put an ionosonde in space? Well, that was Canada's first satellite. Alouette 1 was simply an ionosonde mounted onto a satellite and using the same principle as the ground-based ionosomes, reconstructing the electron density profile from its orbital altitude down to the F2 peak of the ionosphere. So this is up top here is just an example of some of the echoes that we got off the ionosphere from Alouette 1, October 21st, 1962. In addition to that ionosonde data that I talked about before and the incoherent scatter radar data, we also used this data from these original, what we call topside sounders, to construct an empirical model of the ionosphere. And when you do that, you get nice little representations like this. So the plot on the right is just an example of the log of the peak electron density of the ionosphere plotted spatially at a particular given time. I think it's 10 UTC in February 2012. So in this case, the sun is located over here, and you can see there's a substantially larger electron density in the region where we have photoionization towards the sun, then into the night side, or the region that's not sunlit over here. You'll also note this auroral zone here, where we have an enhancement in electron density surrounding the polar cap. In terms of vertical structure, using fit to those data sets as well as some data on the energetic spectra of aurora from another satellite called the SUSY instrument on the DMSP constellation, we're able to really do a great reconstruction here given the red dotted line of the vertical electron density profile of the ionosphere at this particular time, where the black line here is given from an incoherent scatter radar. So you might think, well, project's done. Clearly, we have a good representation of the ionosphere. We're happy with it. We can move on. The problem is that empirical models have a number of caveats. For one, they aren't capable of resolving small scales because they're limited by the spacing of the measurements that were available when we fit these models. So what I'm going to show you here is a movie of the integrated electron density of the ionosphere, or the height integrated electron density of the ionosphere, and the electron density at around the F2 peak in this plot here. The azimuthal direction here is magnetic local time. You can analogize to regular local time. And the radial distance here is the magnetic latitude, or geomagnetic latitude. So I'll play that now. So you can see, one, just from the beginning, there are substantial structure here in the ionosphere. And when we have a geomagnetic storm, what I didn't mention to you before is that Also associated with these storms are strong electric fields and currents that modulate the structure of the ionosphere and can cause substantial, strong drift of the plasma. The plasma can move at velocities as fast as 3 or 4 kilometers per second, depending on the intensity of the event. And as such, this can draw plasma into the pore cap and cause mixing and create a bunch of small-scale structures that we can't really capture with these mostly climatological empirical models. So as I mentioned, despite the abundance of ionospheres, there's still a lack of data over oceans at high latitudes, which is a considerable problem, and we're limited in terms of spatial and temporal scales by the original data sets that we had. On top of that, despite having incoherent scatter radars and the topside sounders, the topside sounder missions ended in the late 70s, and incoherent scatter radars are very few across the Earth's surface. So there are very few observations of the topside ionosphere to use in these models. On top of that, these empirical models are incapable of incorporating indirect measurements. And maybe conveniently enough, we have an abundance of indirect measurements. With the prevalence of GNSS, I mentioned before that GPS signals, or as they propagate through the ionosphere, get slowed down by that medium and can cause an error in your position. Well, if you have a GPS receiver that records 2 frequencies instead of the standard 1, you can actually use that receiver to measure the integrated electron density ionosphere along the ray path of the satellite to receiver or path. This means that these abundant networks of GNSS or GPS receivers on the ground, given by the blue dots here and here, are available, viable, and fairly densely distributed measurements for characterizing the state of the ionosphere. Here we have on the left the GNSS receivers on the ground that are available in near real time within about 2 hours. And on the right we have data from, or the GNSS receivers on the ground that are generally available the next day. So there's a considerable number of these receivers on the ground that are incredible measurements that we can't use for empirical models. Similarly, in situ measurements of plasma density from satellite missions are incapable of easily being, used in the original fitting of empirical models. On the right here, I have a very messy demonstration of a day of orbits of various constellations of satellites that have openly available measurements of electron density at the satellite location. You can see these measurements have great coverage across into the oceans and at high latitudes that would really be a considerable aid to our representation of the ionosphere if we could have incorporated them into these empirical models. Nothing to fear, though. Instead of incorporating these measurements directly into the models when we create them, we can, however, assimilate those measurements into those models at a later time. What I'm plotting here, the black solid curve here and here, is the electron density profile that we get from each shame. The blue curve, unfortunately, is the true measured electron density profile of the ionosphere from an incoherent scatter radar. The red, fortunately, is the electron density profile that we get from my model after assimilating in GPS and satellite in situ measurements. And you can see that satellite data can considerably change the performance and improve the performance of this empirical model. So to conclude, the ionosphere is a dynamic and complex system that's forced both from above in terms of the sun and energetic particles from the solar wind, and from below in terms of waves from the lower atmosphere. New satellite missions like what will hopefully be coming as the Geospace Dynamics constellation in the US, as well as commercial constellations like Spire of these CubeSat missions, show great promise in allowing us to improve our understanding of the ionosphere and increase our capacity to mitigate the effect of the ionosphere on navigation and communications technologies. Signals and measurements of opportunity through citizen science engagement, like programs that are called the HAMSci or Orosaurus, are already showing that by engaging the community of I guess ionospheric fans, we can substantially improve our understanding of the ionosphere. With that, I'd just like to say thank you. You can download eShame or use its web interface at the link here. If you're interested in that HAMSci thing I just mentioned, or in HF communications in general, you can check out this HAMSci link here. It's a nice community of ham radio operators that are coming together to try and produce an interesting data set that can help us understand the ionosphere. If you're an auroral chaser, you can contribute to scientific understanding and also to fellow aurora chasers' observations by checking out Orosaurus at orosaurus.com. Or if you want to check out more videos of the aurora from Yellowknife, you're more than welcome to look at them on the Canadian Space Agency website given by the Aurora Max product here. Finally, feel free to contact me at d.art.timmins@bam.ac.uk for questions about the ionosphere or anything else that you'd like to talk about. Thank you.